Welcome back. This is part two of the Biology 6 Cardiovascular System lecture. At the end of the part one lecture, we just finished we finished off capillaries. So I want to mention where we go next in the lecture outline. We're going to begin this lecture, the part two lecture, by going slightly backwards in the lecture outline. If you look at your lecture outline, just before the capillaries part, there's another part on blood vessels. It begins by saying blood vessels are the tubes that carry the blood, and then it talks about the parts of the blood vessels like the lumen, the tunica interna, the tunica media, and the tunica externa. Well, this next part basically focuses in on the tunica media. Remember, that's the part of the wall of the blood vessels that contains smooth muscle. And it says in the lecture notes there that the tunica media controls the blood flow by changing the size of the lumen. And so that's where we're going to begin this lecture, talking about some details about exactly how and why the tunica media controls the blood flow by changing the lumen size.
Remember that the walls of the arteries and veins have these three tunics: the tunica externa, the tunica media, and the tunica interna. Here we go. So here's an artery right here, and you could see it's tunica interna is the golden colored epithelial tissue there, tunica media there, the red colored smooth muscle, and tunica externa, this dense connective tissue there. And yeah, we see those same tissue layers here in the vein, but of course, remember the veins, the tunica media, the smooth muscle layers is a lot thinner than it is in arteries. Okay, now, when we talked about the arteries and veins, recall that the reason why the arteries have such a thick tunica media is to regulate the blood flow to the organs. So if the body, for whatever reason, decides that this organ needs less blood flow, the way it works is like this. The tunica media of the artery that's carrying blood to that blood vessel, the tunica media squeezes the lumen to a smaller size, and that reduces the blood flow to that organ. And it's just like when you're doing gardening, if you're watering some plants here, and for whatever reason you decide you want less water flowing to those plants, you can squeeze on the hose. And yeah, that makes the lumen of the hose smaller, and so less water comes through, and well, that's how you reduce the water flowing to that plant. So same idea here, that the arteries can squeeze the lumen to a smaller size using their tunica media to reduce blood flow to the organ. And alternatively, if the body decides that organ needs more blood flow, the body can relax the tunica media of the artery carrying blood to the organ, and then just like relaxing your grip on the garden hose, that allows more blood to flow. Okay, so let's see that in action. And just to pick an example, let's say that this organ right here are some muscles in your body, and let's say that you decide to do some exercise. And so don't be afraid to be obvious. Do you think the blood flow will increase or decrease to your muscles as you're exercising? It'll increase, right? Because your muscles need more energy when you're exercising, so the body wants to increase the flow of blood to your muscles when you're exercising. But let's say this organ represents your digestive system organs. Your digestive system organs use a lot of energy and blood flow, and so when you're exercising, your body wants to reduce the amount of blood flow to your digestive system organs, since that blood flow is better used to flow to your muscles. And so, yeah, so when I click the button, this will be like an exercising situation. What we're going to see is the arteries going to this organ, the digestive system organs, will constrict to a smaller size to reduce the blood flow to it, and the arteries going to this organ, which represents your muscles in this example, will get larger to allow more blood flow to the muscles. And let's see, did it work? Oh, I got it backwards, sorry. So this is the organ that's getting less blood flow. So you can see the body, the tunica media of those arteries squeezed to a smaller size. And this is the organ that was supposed to be getting more blood flow. You could see that the tunica media relaxed to make those arteries larger to carry more blood flow. And let me give you another example of the same concept. When you're frightened, what do you think happens to the blood flow of your heart? Increase or decrease? Increase, because when you might need to run away or fight whatever is frightening you, and so your body wants your heart to have more blood flow so it can pump more blood more efficiently. So the arteries that carry blood to the heart get larger or smaller when you're frightened. What do you think? Which is going to make more blood flow to the heart? The arteries getting larger or the arteries getting smaller? Larger, right. Yeah, so I don't have the cartoon of it. Actually, well, maybe I'll just go back to that other cartoon. Here it is. Yeah, so when you're angry or frightened, the arteries that carry blood to your heart, their tunica media relax, so you get more blood flow to the heart. And have you ever heard when people get frightened, they get pale, their skin gets whiter? That happens, and just like you see here, the reason why it happens is the blood vessels that go to the skin contract when you're frightened. The arteries that go to the skin contract when you're frightened. So there's less blood flow to the skin, and that tends to make it paler when you're frightened. Matter of fact, looking at this poor woman here, it almost looks like she's gotten sort of pale from this monster that's frightening her. And here's yet one more example. When people exercise, their skin gets kind of red, especially around their face. That reddening of the skin when they exercise has a name. It's called erythema. I guess we talked about that when we did our chapter on the skin. Anyway, it's called erythema, and what it is the body's trying to put more blood into the skin when you exercise to get rid of body heat, to get rid of excess body heat. And so that's yet another example of the body regulating blood flow. When the body senses that you're getting too hot, it makes makes the arteries going to the skin larger, and so more blood flows to the skin and helps you get rid of body heat that way. Anyway, the whole point of this last 5 minutes is that your body can regulate blood flow to the organs from the arteries either contracting their tunica media or relaxing their tunica media. All right, well, let's say we finished with blood vessels for now. In your lecture handout here on the cardiovascular system, the next topic is the heart rate, and your heart rate is defined as how many times your heart beats per minute. In other words, the heart rate is just beats per minute. For an average adult, when the adult is at rest, not exercising, the average person's heart rate is 72 beats per minute. And, of course, that's just an average. Your resting heart rate might be 83 beats per minute, and the person sitting next to you, maybe their resting heart rate is 64 beats per minute or something like that. I don't know. But on average, for adults when they're resting, it's 72 beats per minute. Now, if you're no longer resting, if you decided to get up and start exercising, what happens to your heart rate? Goes up, right? Because your body, especially your muscles, need more blood flow, so your body would increase your heart rate. But what I'm saying is when you're at rest, on average, 72 beats per minute is your heart rate. And that's also, I should have said, I don't know if I put it there, but that's the adult resting heart rate. For younger people, it's higher. For newborn babies, for example, their resting heart rate is almost twice that it is, so around 130 beats per minute for infants. But as those babies grow and eventually become adolescents and young adults, their heart rate slowly slows down, and so that by the time they reach adulthood, it's on average the 72 beats per minute. All right, well, let's see. Oh, yeah, that's not what I was going to show. Here we go. So what sets a person's heart rate? Well, you might remember that inside your heart are some special tissues called the conducting tissues of the heart. These are the ones that are shown in golden in this photograph right here. And you find these conducting tissues all throughout the heart, but there were two special clumps or nodes of those conducting tissues that I wanted you to know by name. This one is the what? SA node, and this one is the AV node. Good. Notice that they're both in the right atrium. And let's focus on the SA node. You might remember the SA node only has direct control of the, oh, maybe I should say what do these conducting tissues do? They generate and carry the contraction and relaxation signals for the chambers in the heart. They make the electrical signals that cause the chambers to contract and relax. Okay, so what I was about to say is the SA node has direct control over the atria. You can see the little black arrows there showing that the SA node sends out contraction and relaxation signals to the atria. But nevertheless, the SA node is sometimes called the pacemaker of the heart because the rate, the number of contractions and relaxations per minute that it sends to the atria is also the same rate that the ventricles are contracting and relaxing. And so in that sense, it sets the overall heart rate. And so you may say, well, if the SA node only controls the contracting and relaxing of the atria, how is it that the ventricles have the same rate? Well, the answer is this other node, the AV node. Remember, the way it works is that every time the SA node sends out a signal to the atria, the AV node intercepts that signal. You can see the little black arrow going to the AV node. And then after delaying briefly, the AV node sends that signal on downward eventually to the ventricles. And so that in that way, the ventricles stay at the same rate as the atria. And I think I made an analogy like in a band. Think of the SA node as the drummer and the atria are the drums. And so like the drummer only has direct control over the drums because that's the instrument he plays. But nevertheless, the guitarist, which we'll think of as the AV node, and the ventricles are the guitar, the guitarist, the AV node, listens in on the rhythm that the drummer's playing, and of course the guitarist then keeps his own rhythm the same as the drum's rhythm, and so in that way the AV node keeps the ventricles beating at the same rate as the SA node is making the atria contract and relax. And so in that sense, the SA node is the pacemaker for the entire heart, in the same sense that the drummer sets the pace for the entire band. Okay, so what was the point of all that? Well, just that the SA node is the pacemaker of the heart, and so the rate that the SA node is firing out contraction or relaxation signals is what determines what your heart rate is. Now, so that being said, the SA node is willing to change the rate that it makes the heart beat depending on stimulation it gets from the nervous system. If you remember the chapter on the nervous system, there was a part of the nervous system called the autonomic nervous system. And you might remember those are motor neurons that send signals to control involuntary muscles like smooth muscle and cardiac muscle. So there's a part of the autonomic nervous system that synapses with, that's connected to the SA node, and that part of the autonomic nervous system is called the sympathetic division. That's the part of the autonomic nervous system that fires off more signals, more nerve signals when you're angry or frightened. And so yes, so when you're angry or frightened, your sympathetic division motor neurons send off more signals, and when the SA node gets those signals from the sympathetic division, it increases your heart rate. And that matches our experience, right? When you're angry or frightened, your heart rate speeds up. Well, there's this other division of the autonomic nervous system, the parasympathetic division. Those motor neurons send off more signals when you're calm and relaxed and peaceful. And so when you're in that state, calm and relaxed and peaceful, the parasympathetic division sends more signals to the SA node. And so what happens then? Well, your heart rate slows down. And so those are two major things that control your heart rate, the sympathetic and parasympathetic division, speeding up if you're angry or frightened, and slowing it down if you're calm and peaceful. There are some other things that can also affect your heart rate in addition to the sympathetic and parasympathetic division neurons. One thing that can affect it is whether you're male or female. Women tend to have slightly higher heart rates than men on average. It's not a huge difference, but the average woman's heart rate is 80 beats per minute. I should say relaxed adult woman, 80 beats per minute, as opposed to the average for men and women together of only 72 beats per minute. Now you may wonder, well, why do women have a slightly higher heart rate than men. I guess I don't really know the answer to that question, but it's just some difference in our metabolisms. Younger people tend to have higher heart rates than older people. I guess I already mentioned that for adults, it's the average of 72 beats per minute. But the younger you are, the faster it tends to be. And I think I mentioned newborn babies, their resting heart rate is around 130 beats per minute. In addition to all that, there are also some ions in your blood that can affect your heart rate. These are three of the major ones: sodium ions, potassium ions, and calcium ions. Why these particular ions? Well, the tissues of the heart, the cardiac muscle cells, and those conducting tissues of the heart use these ions for depolarization and repolarization. In other words, for their electrical contraction or relaxation signals. And so if these ions are not at their proper concentrations in your blood, the heart tissues are not going to be getting the right concentrations of them, and so the heart tissues are not going to be able to beat at their normal rhythm. And so in some cases, if these are not at their proper concentrations, it can cause the heart to beat faster, or if there are other non-normal concentrations, it might cause the heart to beat slower. And if they are even different non-normal concentrations, it might cause the heart to lose its rhythmic beating, where the heart is still beating, but it has arrhythmias. It's not keeping a steady beat. And if they're really, really, really far outside their normal concentrations, it can cause the heart to stop beating entirely, just basically go into cardiac arrest, and, well, then you'd be dead in a few minutes. Oh, and one more thing that can affect your heart rate: exercise, of course. I guess I mentioned that already. If you're exercising, your muscles need more blood flow so they can make energy by aerobic respiration. So when you're exercising, your heart rate increases. There we go. But there's actually kind of an interesting effect. If you exercise a lot, so you become physically fit, yeah, your heart rate goes up when you're exercising. I mean, that happens to everybody, whether you're fit or not. But if you're physically fit, your resting heart rate is lower than an average person. And I know that sounds a little confusing, so let me say it again. Everybody, whether they are physically fit or not, their heart rate goes up if they're exercising. But if you're athletic, if you're physically fit, your resting heart rate, your non-exercising heart rate, tends to be lower than an average person's resting heart rate. And the more physically fit you are, the lower it's going to be. And so everything else being equal, a lower resting heart rate is a good sign. It shows that you're physically fit. I think that's Lance Armstrong there. He was, I think for a while, I would say he was probably the most fittest person in the world. He won the Tour de France bike race, I guess 6 or 7 times. His resting heart rate was 33 beats per minute, which is, you should be astounded by that. I mean, that's less than half of what a normal person's resting heart rate is.
But didn't he take?
He took a bunch of illegal drugs, yeah.
Would that do anything to the body to help him?
Yes, so what he took was actually, I think I mentioned it in a previous lecture, there's a hormone called erythropoietin, which increases the number of red blood cells you have in your blood, so therefore your blood can carry more oxygen, and so that's the drug he took. But even that being said, he was still very physically fit.
No, yeah.
And so
I just wanted to know if the drug was
yeah. From my understanding, the erythropoietin definitely helps athletes by boosting their red blood cell count.
Does that harm his body?
It must, because I think that's why they make it illegal. I probably think any time you're changing what your body wants to do by introducing artificial drugs, it's probably not good for your body. But anyway, the point I was making is, even despite taking the erythropoietin, he was very physically fit, and as a result, he had this incredibly low resting heart rate.
Okay, so hopefully you have a good understanding of the heart rate, but the heart rate is just one measure of how hard the heart is pumping blood. In other words, if a person's heart rate is high, then their heart is pumping more blood, and if their person's heart rate is low, then their heart is pumping less blood. But there's another measurement, a different measurement of the heart's activity of pumping blood, and it's called the stroke volume, and that's what we're going to talk about now. So stroke volume is defined as the amount of blood expelled from each ventricle per beat, per heartbeat. And so to understand what stroke volume is, to understand what that definition means, let's imagine that we can stop the cardiovascular system, stop the heart for a moment. And then let's imagine we can tell the heart to beat. Somehow we can command the heart. And we say, okay, heart, we want you to beat just one time. And so the heart's going to do that for us. Watch it here. Squirt. Well, so in that one beat, the heart squirted out a certain volume of blood, right? And that volume of blood that the heart squirted out in that one beat is called the stroke volume. So yeah, it's the amount of blood expelled from one ventricle of the heart per beat is the stroke volume. On average, for an average adult at rest, the stroke volume is about 70 milliliters of blood per beat. Now, how much is 70 milliliters? It's about a third of a cup of coffee. So, on average, for a resting adult, their stroke volume, the blood that squirts out of each ventricle per beat, is around 70 milliliters. That's their average resting stroke volume. Okay, and so here comes the next heartbeat. Squirt, there's the stroke volume, probably around 70 milliliters. Here's the next beat, another stroke volume, squirt of around 70 milliliters per beat. Okay, yeah, so for an average person, stroke volume, 70 milliliters per beat. But as it turns out, a person's stroke volume can change. And you might wonder, well, how is that? Well, the major thing that can affect what the stroke volume is, how much blood squirts out of the heart per beat, is the force of contraction. The stronger the force, the stronger that the cardiac muscle contracts, the larger the volume of blood that gets squirted out. In other words, the larger the stroke volume, the harder the the harder the force of contraction of the heart muscle, the larger the stroke volume on that beat, and vice versa. The less strongly, the weaker the contraction of the heart muscle, the smaller the stroke volume is going to be on that beat. And that sort of makes sense. If you think about making an analogy with squeezing on a wet sponge, imagine soaking a sponge under your kitchen faucet so the sponge gets full of water. And I think you can see that if you squeeze very softly on that wet sponge, a relatively small volume of water will be squeezed out of it. But if you just squeeze as hard as you can on that wet sponge, a larger volume of water will be squeezed out of it. Well, that's the concept that we're talking here. The stronger the heart muscle contracts, the larger the stroke volume. The more blood is going to be squirted out on that heartbeat, and the more weakly the heart muscle contracts, the less blood is going to be squirted out. So the smaller the stroke volume on that beat. Now, you might wonder, well, okay, but I understand that the strength of the heart muscle's contraction controls the stroke volume, but you might wonder, well, what exactly would cause that? Why would the contraction of the strength of contraction of someone's heart muscle change? Well, there can be several reasons that might change the contraction strength of the heart muscle and therefore change the stroke volume. Here's one example. Athletes have very strong hearts, and that makes sense because they're out jogging or running or bicycling, whatever their sport is. But yeah, when they're exercising, they're making their hearts work hard, right? And I think you would agree that if you work out any muscle, that muscle's going to get stronger, right? And the heart is a muscle; it's a muscular organ. So these athletes, because they work out all the time, end up with strong hearts. In other words, their hearts are stronger, so their hearts have a naturally a strong force of contraction. So think about what that means. Since athletes' hearts get strong, their hearts are going to contract with more strength than an average person's heart on every heartbeat. And since strength of contraction affects stroke volume, athletes are going to have a larger stroke volume than an average person. Athletes, in other words, are going to have a stroke volume much larger than the 70 milliliters per beat of an average person. Yeah, so notice that's a bigger arrow than I showed on the last one. So yeah, with athletes, because they work out their heart so much, they get a stronger heart, and so it just contracts more strongly with every heartbeat. So athletes have a larger stroke volume per beat than an average person does. There's another thing that can also change the stroke volume, change the strength of contraction, and therefore change the stroke volume. And it's something called the end diastolic volume. What the end diastolic volume means, it's the volume of blood that returns to the heart with each heartbeat. So let me show it like this. So here's my diagram of the heart, and of course, you know that the heart returns to the atria of the heart. I should say the blood returns to the atria of the heart, and so this vessel right here, which is one of the pulmonary veins, returns blood to the left atrium of the heart, and these are the superior and inferior vena cava, which return blood to the right atrium of the heart. So I'm going to use just the blood returning to the left atrium in this example that I'm about to show you of the end diastolic volume. But everything I'm showing you here also would apply to the blood returning to the right atrium, but just to keep the diagram simple, I'm just going to show it on one atrium. Anyway, so the blood that returns to the heart from every heartbeat is called the end diastolic volume. And to begin with, I'm just going to show that volume of blood, the end diastolic volume, as 70 milliliters. So 70 milliliters of blood is returned to the heart on that heartbeat, and so the end diastolic volume is 70 milliliters. Now, you know that in the cardiac cycle, the atria contract to fill the ventricles with blood, so that end diastolic volume of blood, that 70 milliliters, then gets put into the ventricles when the atria contract. And now you know that the next step in the cardiac cycle, of course, is for the ventricles to contract, so that volume of blood, that 70 milliliters, that end diastolic volume from the previous beat, now gets squirted out of the heart when the ventricles contract, like that. So notice that the volume of blood that returned to the heart, that 70 milliliters end diastolic volume, was exactly what the heart squirted out on the next beat, right? The volume of blood that returned to the heart was exactly the volume of blood that the heart squirted out on the next beat. And so let's imagine that for whatever reason, a larger volume of blood returns. Let's say now that on this beat, 100 milliliters of blood returns to the heart. So we'd say that the end diastolic volume was 100 milliliters. Well, that's what the ventricles would squeeze out. The ventricles would then contract a little bit harder to be sure that they expelled that volume of blood that came back on the previous beat, the 100 milliliters of blood. So, to expel that larger volume of blood, that 100 milliliters, the ventricles would have to contract a little harder, right? Because strength of heart muscle contraction is what sets the stroke volume, the amount of blood that's expelled from the heart. Now let's imagine that for whatever reason, an even larger volume of blood returns to the heart from the heartbeat. Let's say that the end diastolic volume, the amount of blood that returned to the heart, was now 130 milliliters. And so, of course, that would get squirted down from the atria into the ventricles, and now it's time for the ventricles to contract. Well, the ventricles would contract even harder so that they can expel 130 milliliters of blood on this next heartbeat, like that. So the lesson here is that the heart automatically adjusts the stroke volume to match whatever the end diastolic volume was. In other words, the heart muscle adjusts its strength of contraction to expel exactly the amount of blood that returned to the heart from the previous heartbeat. In other words, saying the same thing still yet again, the end diastolic volume, however much blood returns to the heart from the previous heartbeat, is exactly the amount of blood that the heart expels on the next heartbeat. And so for the heart to adjust how much blood it expels on each beat to match the end diastolic volume from the previous beat, the heart muscle has to adjust how strongly it contracts, right? So that's the big picture of this part of the lesson, that the higher the end diastolic volume, the larger the stroke volume of the next beat is going to be, so that the heart can always expel the amount of blood that it received from the previous beat. If it receives 70 milliliters, the end diastolic volume was 70 milliliters, then the next heartbeat, the heart muscle will contract with just enough strength to expel 70 milliliters. And so the stroke volume would be 70 milliliters on the next beat. If the end diastolic volume on a particular beat was 100 milliliters, the heart muscle will contract so that with enough strength so that the next stroke volume is 100 milliliters. So this concept that the heart automatically adjusts the stroke volume from beat to beat to be sure that it always expels the same volume of blood that returned to it from the previous beat. That concept has a name. It's called Starling's Law of the Heart, which I always thought had kind of a poetic ring to it. But yeah, it means just what I was saying here. The higher the end diastolic volume, the larger the stroke volume, so that the heart can expel that amount of blood, and conversely, the lower the end diastolic volume, the lower the stroke volume is going to be on the next beat, again, so that the heart can always expel the same amount of blood that returned to it on the previous beat. Okay, well, just to review, so far we've discussed two measurements of how hard the heart is pumping blood. We've talked about heart rate and we've talked about stroke volume, right? Well, there is yet another measurement of the heart's pumping activity, and it's called cardiac output, or CO for short. The cardiac output is defined as the amount of blood pumped out of each ventricle per 1 minute. To understand, to be able to picture exactly what cardiac output is, let's imagine, like you see here, that the heart is pumping blood, and let's imagine that we had some way to measure how much blood, the volume of blood pumped out of one ventricle per minute. And I'm going to use the left ventricle as my example, but I could just as well use the right ventricle. Anyway, yeah, let's imagine we had some method of measuring exactly what volume of blood that ventricle there, the left ventricle, pumped in 1 minute. So that would be the cardiac output. It's milliliters of blood pumped out of one ventricle per minute. Now, there is an equation for calculating the cardiac output from the person's heart rate and their stroke volume. In other words, there's an equation that relates cardiac output to heart rate and stroke volume. And here it is. The person's cardiac output is equal to their heart rate multiplied by their stroke volume. And if you think about it, the units kind of make sense. Heart rate is beats per minute, and stroke volume is milliliters per beat. And so if you multiply how many heartbeats they have per minute by how many milliliters the blood that the heart expels per beat, that's going to give you how many milliliters the heart expels per minute, and that's what stroke volume is. And I want you to be able to use this equation. I want you to be able to calculate the cardiac output if I give you a person's heart rate and their stroke volume. And let's practice doing this calculation just using an average heart rate and an average stroke volume. So let's imagine an adult at rest. Who remembers what a resting adult's average heart rate is? And you're right. The answer is 72 beats per minute. And who remembers for an average resting adult what their stroke volume is? How many milliliters of blood the heart pumps per beat? And that's right. For an average resting adult, the stroke volume is 70 milliliters per beat. So if we want to find the cardiac output of an average resting adult, we multiply those two numbers together, and mathematically that comes out to 5,040 milliliters per minute. Yes, so 5,040 milliliters per minute is an average resting adult's cardiac output. That's how many milliliters of blood their heart pumps each minute. But of course, that's just an average number, and it varies from one person to another. So I'm saying that not everybody's heart has to pump exactly 5,040 milliliters per minute when they're at rest. For one person, maybe their cardiac output might be 4,400 milliliters per minute, and for a different person, maybe it's 5,350 milliliters per minute, and for a different person, it might be 5,932 milliliters per minute. It varies from person to person, just like heart rate varies from person to person, and stroke volume varies from person to person. But I am saying that on average, for most resting adults, their resting cardiac output is in the neighborhood of 5,000 milliliters of blood pumped by the heart per minute. We now have three measurements of the heart's activity, right? We can talk about the person's heart rate, beats per minute. We can talk about what their stroke volume is, how many milliliters of blood their heart pumps per beat. And we can now also talk about cardiac output, how many milliliters of blood their heart pumps per minute. Well, of those three, the heart rate, the stroke volume, and the cardiac output is the meaningful measurement of the body's tissues being adequately supplied with oxygen. And when I say the meaningful measurement, I mean the best of those three. So I'm saying that the cardiac output is the best measurement of the body's tissues being adequately supplied with oxygen. So here's what I'm saying. So that the major job of your blood is to carry oxygen all throughout your body because your tissues need that oxygen to be able to keep themselves alive doing cellular aerobic respiration. And the heart, of course, is what pumps that blood throughout the body to supply your tissues with oxygen so they could stay alive doing cellular aerobic respiration, right? So what I'm saying is you can't judge by a person's heart rate whether their tissues are being adequately supplied with oxygen. In other words, if you ran into a person and they happen to have a low heart rate, you can't judge just by their heart rate whether their tissues are being supplied with enough oxygen. And like the same thing goes for stroke volume. If you found a person, let's say, who had a lower than normal stroke volume, you can't judge by that alone whether their tissues are adequately being supplied with oxygen. But cardiac output is a good indicator of how much oxygen their body is being supplied with. Cardiac output, that's why I'm saying it's the best indicator of how much oxygen their tissues are being supplied with. Let me give you kind of an example of this. So yes, when we're resting, our an average person's cardiac output is around 5,000 milliliters per minute. But when we exercise, of course, our body needs more oxygen. Our tissues need more oxygen, especially the muscle tissue, right? Because when you're exercising, your muscles are using a lot more energy, so they have to do a lot more cellular aerobic respiration. So your muscles need a lot more oxygen when you're exercising. So when we exercise, the body increases the cardiac output to increase the amount of oxygen delivered all throughout the body. And actually, let me show you a graph of this. On the y-axis of this graph, this shows the cardiac output. And so right from there to there on this y-axis is the cardiac output when the person is resting. But when the person is exercising, that's now their cardiac output on this y-axis over here. So you can see when you're exercising, the cardiac output is a lot higher than when you are resting. In some athletes, their cardiac output can be 7 times larger when they are exercising than when they are resting. But even if you're not, a world-class athlete, your cardiac output still goes up higher than your resting. Your exercising cardiac output is still going to be higher than your resting cardiac output. And again, why? Well, it's because when you're exercising, your body, especially your muscles, need more oxygen. And so what I'm saying is that's why your body increases the cardiac output when you're exercising, is because cardiac output is the meaningful measurement. It's the best measurement of how much oxygen your body is supplying to its tissues. Okay, now be careful here. I'm not saying that the definition of cardiac output is how much oxygen your body is supplying to the tissues. The definition of cardiac output is exactly what I wrote in your lecture outlines. It's the amount of blood, the volume of blood pumped out of each ventricle per minute. But I'm saying that of cardiac output, stroke volume, and heart rate, it's the cardiac output of those three measurements that's the best indicator of how much oxygen is being supplied to the body. And that's using this to sort of show you that sure, when you're resting, your body needs less oxygen, and when you're exercising, your body needs more oxygen. And you can see that it's the cardiac output that's increased when you're exercising relative to when you're resting. Okay, well, getting back to our equation, cardiac output equals heart rate times stroke volume. As I said, I want you to be able to solve this equation. If I give you a person's heart rate and give you a stroke volume, I want you to be able to multiply those two to tell me what their cardiac output is. And let me give you a sample problem here. So here's the gentleman who's jogging. His name is Mark, let's say. And let's say, well, Mark is jogging. His heart rate is 110 beats per minute, And let's say when he's jogging, his stroke volume is 98 milliliters per beat. So I might ask you, okay, what is his cardiac output? And before we do the actual calculation, let me point out something. The body will automatically adjust the cardiac output to meet the body's current oxygen need. And so, for example, when Mark is jogging, his body needs more oxygen, especially his muscle tissues do. His body's oxygen need increases when he's exercising, so his body will increase his cardiac output. And how does the body increase the cardiac output? Your body can change the cardiac output by adjusting the heart rate, like increasing the heart rate, or it can adjust the cardiac output by increasing the stroke volume, or oftentimes it can do both. The cardiac output can be adjusted by the body changing the heart rate and the stroke volume. And we're seeing that here. When he's exercising, notice that his heart rate is above the average of 72 beats per minute, and his stroke volume is above the average of 70 milliliters per beat. So anyway, this is an example of how the body can adjust the cardiac output to meet the oxygen needs, and the body typically does that by changing the heart rate and the stroke volume, since those are what multiply to the cardiac output. So here's Mark, and my problem to you is this. His heart rate is 110 beats per minute. His stroke volume is 98 milliliters per beat, when he's jogging. What is his cardiac output? We're going to use our standard equation here. Cardiac output equals heart rate times stroke volume. His heart rate is 110 beats per minute. His stroke volume is 98 milliliters per beat. So we multiply those two together, and we get 10,780 milliliters per minute. That's how much his heart is pumping per minute. And again, notice that's higher than an average resting adult's cardiac output of 5,000 milliliters per minute, because he's not resting. So his body had higher oxygen need, so his body made the cardiac output higher than average because his body needs more oxygen when he's jogging. All right, so hopefully you have a good idea to how to use the cardiac output equals heart rate times stroke volume equation. But I now want to discuss a slightly different situation than we just looked at when Mark he was jogging. So in that situation, his body had a higher demand for oxygen, so his body increased the cardiac output by increasing his heart rate and stroke volume. But the different situation that I want to talk about right now is this. Imagine that the person's body had a normal average demand for oxygen. So, the person's cardiac output is supposed to be around 5,000 milliliters per minute. In other words, let's say the person is resting. We're imagining, that the body's need for oxygen is normal, and it's not changed. The person's not exercising or anything like that. But let's say in that situation, the person's heart rate or the person's stroke volume has changed. So what would happen? Well, what I'm saying is that if the person's demand for oxygen is normal, then their cardiac output is going to be somewhere around 5,000 milliliters per minute, right? But if in that state their body's need for oxygen has not changed, something makes the stroke volume change, then what I'm saying is the body will automatically adjust the heart rate so that those two still multiply to 5,000. Or in other words, another example, let's say the person's resting, so again their cardiac output's supposed to be around 5,000, and let's say something makes the heart rate change, then the body will automatically adjust the stroke volume to compensate for that change so that the two numbers still continue to multiply to around 5,000. And maybe an example might be good here to illustrate what I'm talking about here. Okay, so let's imagine an athletic person, some sort of athlete. And from what we've talked about a few minutes ago, when an athlete is exercising, when anybody's exercising, their body's demand for oxygen increases. So their body's going to increase their cardiac output while they're exercising. But here's the thing. For everybody, for all adults, when they're resting, their cardiac output is supposed to be around 5,000 milliliters per minute. So I'm saying it doesn't matter whether a person's an athlete or a non-athlete. When they are at rest, their cardiac output is going to be around 5,000 milliliters per minute, because that represents, the amount of oxygen that an average person's body needs when they're at rest, and the oxygen that the body needs when a person is resting really is not affected by whether they're an athlete or not. Anyway, so this person's an athlete and they're resting, so their cardiac output is supposed to be around 5,000 milliliters per minute, is what I'm saying. But from what we talked about earlier, that athletes have a stronger heart tissue than an average person, right? Because when athletes exercise, they're exercising their heart. And so like any other muscle, the heart gets stronger. And so let's review this together. If a person's heart muscle gets stronger, let's say because they're an athlete, what's that going to do to their stroke volume? What's that going to do to their milliliters of blood pumped per beat? And the answer, hopefully remember, is the stroke volume increases. The stroke volume is affected by the strength of the heart contraction. So what I'm saying is athletes have stronger hearts, and so their stroke volume is going to be higher than an average person. And that's true even when they're at rest. Their hearts get stronger all the time. So even when the athlete is at rest, their stronger heart's going to cause an above average stroke volume. And so that's kind of the key to understanding what we're going to see next. So, for everybody, their cardiac output is from their heart rate multiplied by their stroke volume. And so for that athlete we just saw, when she's at rest, her cardiac output is supposed to be around 5,000 milliliters per minute. But because she has this super strong heart, because she's an athlete, her stroke volume is going to be larger than an average person's stroke volume. So let's think about this mathematically. If two numbers are supposed to multiply to 5,000 and one of those numbers gets bigger, which is what we're seeing here, what has to happen to the other number so that the two numbers continue to multiply to 5,000? And you're right, the other number has to get smaller, right? If two numbers are supposed to multiply to 5,000 and something makes one of those numbers get bigger, you have to make the other number smaller so that they continue to multiply to 5,000. Yeah, so in athletes, because their heart is strong, their stroke volume gets larger than an average person's, larger than 70 milliliters per beat. And so their body automatically reduces their heart rate to compensate for the increased stroke volume so that the two numbers continue to multiply to 5,000 when the athlete is at rest. And so that's what I was trying to say. If you look at the lecture outline, it says if the body's need for oxygen has not changed, the person's resting, so they need around 5,000 milliliters per beat. If the body's need for oxygen has not changed, but one of the factors, let's say the stroke volume in this example, has changed, and the stroke volume's gotten larger, then the heart automatically adjusts the other factor, the heart rate in this example, in the opposite direction. The heart rate got smaller automatically so that the two continue to multiply to the normal cardiac output. Let's do an actual mathematical example of such a thing here. So here's this athletic woman, Maya's her name, and let's say that when she's at rest, her stroke volume is 104 milliliters per beat, and her cardiac output is around 5,000. Let's use 4,800 milliliters per minute. Again, let me point out that notice her stroke volume is higher than average. The average stroke volume is 70 milliliters per beat, and you know why, because she's an athlete, so she's given herself a strong heart. So with every contraction, the heart is going to just squeeze harder. So with every contraction, she has a higher than average stroke volume. Anyway, so here she is resting. Her resting stroke volume is 104 milliliters per beat, and just like an average person, her resting cardiac output is going to be around 5,000 milliliters per minute. Let's say 4,800, and I'm going to ask you, calculate her heart rate. What is her heart rate given that her stroke volume is 104 milliliters per beat and her cardiac output is 4,800 milliliters per minute? Well, so I've given you this equation, but there's a slight problem here. This equation is for finding the cardiac output when I give you the heart rate and the stroke volume. And that's not what you're doing in this problem. In this problem, you're trying to figure out the heart rate after I've given you stroke volume and cardiac output. Well, not a problem. There are two rearranged forms of this equation that you can use. So these basically represent the same equation as up here, but they're just slightly rearranged. These equations are heart rate equals cardiac output divided by stroke volume, and stroke volume equals cardiac output divided by heart rate. So when I'm giving you problems that involve cardiac output and heart rate and stroke volume, whatever I'm asking you to find, like I might ask you to find cardiac output or heart rate or stroke volume, whichever I'm asking you to find, use the equation for the thing that I'm asking you to find is on the left-hand side of the equal sign. So if I give you a problem where I say find the cardiac output, use this equation because that's the equation where cardiac output is to the left of the equal sign. If I give you a problem where I ask you to calculate the heart rate, use this equation because that's the equation where the heart rate is to the left of the equal sign. And if I give you a problem where I ask you to calculate the stroke volume, then use this equation because this is the equation where the stroke volume is to the left of the equal sign. Okay, yeah, so in this problem, I'm asking you to find Maya's heart rate, and so this is the equation you're going to use, and this equation tells you to find the heart rate, you divide her cardiac output by her stroke volume. So let's do that. Her cardiac output is 4,800 milliliters per minute. Her stroke volume is 104 milliliters per beat. So we divide her cardiac output by her stroke volume. In other words, we divide 4,800 milliliters per minute by 104 milliliters per beat, and that gives us her resting heart rate, which is 46 beats per minute. Good. Yeah, so be able to do problems like that. If I give you a person's cardiac output and I give you their stroke volume, be able to calculate their heart rate. Now let me point out something here. Notice that her resting heart rate is a lot lower than an average person's, right? What is an average person's resting heart rate? 72 beats per minute. Yes, so this is an indication of fitness. That her lower than average resting heart rate is not an indication that she's unhealthy, just the opposite. The more fit a person is, the lower their resting heart rate is going to be. The name for that phenomena is called athlete's bradycardia. Bradycardia means a slow heart rate. Yes, and so it's actually a sign of fitness. For athletic people, the lower their resting heart rate, the more fit they are. And again, you can understand why, because for anybody, their resting cardiac output, any adult, their resting cardiac output is going to be around 5,000. But for athletes, their stroke volume is higher than an average person's because athletes have stronger hearts. So to compensate for the higher than average stroke volume, athletes' hearts automatically lower their resting heart rate so that the two continue to multiply by to around 5,000. Anyway, so yeah, be able to calculate heart rate if I give you a person's cardiac output and stroke volume. Let's do another problem along these lines. Some people end up with weakened hearts. There are various types of diseases that can cause a person's heart to get weak. And we'll talk about these a little bit later on in this lecture on the cardiovascular system. But one example is something called congestive heart failure. Anyway, so let's imagine that this person here has something has made his heart weak. Maybe he has congestive heart failure, but his body's demand for oxygen is going to be the same, and so let's imagine that his resting cardiac output is going to be around 5,000. Okay, so before we actually put some numbers into this problem, let's think about what we expect to happen. All right, so we expect his cardiac output when he's resting to be around 5,000, just like any other resting adult. But is his stroke volume going to be larger or smaller than average when he has his weak heart? And the answer is going to be smaller, right? Because remember that stroke volume is controlled by the strength of the heart's contraction. He has a weak heart, and therefore it's going to contract more weakly than a normal person's, and therefore his stroke volume is going to be smaller than normal. Well, if the body needs these two numbers to multiply to around 5,000, and his weak heart made his stroke volume smaller than an average person's, what will the body have to do to his heart rate so that the two numbers still multiply to 5,000? And the answer is increase it, right? If you're trying to make two numbers multiply to 5,000 and one of those numbers gets smaller, you have to make the other number bigger to compensate so that they continue to multiply to right around 5,000. And so that's what we're going to see, but let's actually put some numbers into this problem. Okay, so this gentleman's name is Marvin, and because he has a weakened heart, it has a smaller than average stroke volume, let's say 56 milliliters per beat, and his resting cardiac output is going to be close to normal. So let's say that it's around 5,000 milliliters per minute, because his body's demand for oxygen is about the same as anybody else's. So yeah, let's say his cardiac output is 5,100 milliliters per minute, and I'm asking you, well, what is his heart rate? All right, so again, we're going to use this equation here because remember, if I ask you to find something, like I'm asking you to find the heart rate, find the equation here on this page where the thing you're trying to find, the heart rate in this case, is the thing to the left of the equal sign. So we're using this equation. It tells us to divide his cardiac output by his stroke volume, and let's do that. His cardiac output is 5,100. His stroke volume is 5,100 milliliters per minute. His stroke volume is 56 milliliters per beat. You divide those two, and you get 91 for his heart rate, 91 beats per minute. So again, we're seeing this principle that the heart will automatically adjust either the stroke volume or the heart rate to compensate for a change in the other. If something makes one of these numbers go down, like he has a lower than average stroke volume, the heart will automatically increase the other factor of cardiac output, the heart rate, in the opposite direction, so that the two numbers continue to multiply to a normal, or at least a near normal cardiac output. Okay, so please be able to use any of these equations. If I give you heart rate and stroke volume and ask you to calculate the cardiac output, this is the equation you use. If I give you a cardiac output and stroke volume and ask you to calculate the person's heart rate, this is the equation you use. And if I give you a person's cardiac output and their heart rate and ask you to calculate stroke volume, this is the equation that you use. Okay, this is the end of part 2 of the cardiovascular system lecture. Now please watch part 3.